The History of the Atom, Part 2, by Maile Risch. In 1900, Max Planck used the idea of quanta, discrete units of energy, to explain hot glowing matter. He proposed that the energy is radiated in very minute and discrete quantized amounts of packets, rather than a continuous, broken waves. His theory significantly contributed to the understanding of atomic and subatomic processes. He was able to determine that the energy of each quantum is equal to the frequency of the radiation multiplied by a universal constant that he derived, now known as Planck's constant, which measures the energy of the individual quantum, equal to 6.626 times 10 to the negative 34th power. He describes the behavior of particles and waves at the atomic scale. In 1905, Albert Einstein used Planck's theory to describe the particle properties of light. He created the quantum theory of light, the idea that light exists as particles, he called photons. He invented a new method of counting and determining the size of atoms or molecules given in a certain space. He therefore created an equation, E equals mc squared, meaning energy content of the body is equal to the mass of the body times the speed of light squared. In other words, mass can be changed into energy, and energy can be changed into mass. The speed of light in Einstein's equation is based off electromagnetic radiation. The former process is demonstrated by the production of nuclear energy, when particles are smashed and their energy is captured. The later process is the conversion of energy into mass, which is particle acceleration, when low-mass particles go through a device and become larger. He completed special relativity, which relativity sees light as a continuous field of waves. In 1913, Niels Bohr used Planck's theories to develop a new and more accurate model of the atom. He modified Rutherford's model by requiring that the electrons move in orbits of fixed size and energy around the nucleus. He called this the quantized shell model. The energy of the electron depends on the size of the orbit and is lower for smaller orbits. Radiation can occur only when the electron jumps to another orbit. The atom will stable in the state with the smallest orbit, since there is no orbit of lower energy into which the electron can jump, thus meaning absorbing or emitting a photon with the appropriate precise wavelength. In 1925, Werner Heisenberg proved Bohr wrong. Electrons do not travel in neat orbits. All electrons that contain photons will then change momentum in physics. He calculated the behavior of electrons and subatomic particles that make up an atom. The idea made a better understanding of the patterns of electrons. He noticed behaviors that made electrons alike. He contributed to the atomic theory by including quantum mechanics, which tells the behavior of elementary particles and atoms. In 1926, Erwin Schrödinger took the Bohr model one step further. His model was called the electron cloud model. It can be portrayed as a nucleus surrounded by an electron cloud, where the probability of finding an electron is greatest and less likely to be in the less dense area of the cloud. The model introduced the concept of sub-energy levels, similar to the quantum mechanical model that does not define the exact path of an electron, but does predict the odds of the location of an electron.